and it's perfect spelled Jürgen Bear, but it was perfect. Thank you very much. Okay, good morning, ladies and gentlemen. I want to talk about a little bit strange thing for most of you. Lock-in thermography is not, I think, very well known, and it's a little bit of a dream, I would say. We had the dream to measure the dissipated energy in crack propagation experiments to make a new law, a new description for crack propagation based on this dissipated energy. And then a man came along and said, I have a perfect tool for you. I have a thermographic camera, costs a lot. We were afraid. And then he said, I have a giveaway for you. You get a black box from me, and this black box can split off the signal, the measured temperature, in an elastic part and in a dissipative part. And then we were happy, bought this very expensive thermographic equipment, and we're lucky, made some nice measurements, and then we made one big mistake. We wanted to know what's inside the black box, and we wanted to understand what is going on in this box. And that was the problem. Let me start at first with a little bit of theory to the lock-in thermography. It all depends on the thermoelastic effect. It was introduced by Lord Thomson, 1853, that when you pressurize a material, it's getting warm, and when you put on a tensile stress, it's getting cold. That's all. You have some restrictions. You have to have a linear elastic material. You have the temperature changes must be adiabatic, and the material properties have to be independent of the temperature, and then you can calculate it with this little formula. There is the thermoelastic constant, which is, can be calculated by different parameters of the material, and better is to make this determination of the thermoelastic constant in an experiment. Yeah? And here you see the experiment, you have the stress, and here you have the temperature change. That works pretty well. But now we come to the dissipated energies, and the dissipated energies, there was some experimental work by Bremont and by Sakagami, and they told you get the dissipated temperature change, or the temperature change by dissipated energy, I have to say, with a double loading frequency. And to separate these two parts, you make a discrete Fourier transformation of the signal. Looks like that. You get a mean temperature, you get a thermoelastic part, yeah, and you get an image. When you make it for each pixel of this image, you get a so-called E-mode picture. And for this double loading Fourier frequency, you get the D-mode picture, and that's what inside the black box. Then we made it by our own, and we added some additional parts with 3 times of the loading frequency and 4 times of the loading frequency. That means the higher modes, and you see we get also a signal here, temperature signal, when we have 3 times the loading frequency and even at 4 times, and you get a one at 5 times and so on. And then we thought about, what is that? So we go a step back and looked on, not on cracks, we looked on normal fatigue experiments. And then we get some problems, because the lock-in evaluation is just a decomposition of the material, of the signal into sine waves. And that we have to remember. So we have to look on a signal that we can dissect into perfect sine waves. And that's what the problem is. And here we have the problem. is everything what we measure, can we describe it by a sine wave? And then we had a look on different materials. Here you see an experiment on copper. We measured the temperature signal and dissected it with the DFT mode into the dissipative part, and we subtracted just the elastic part, and we get the red curve. And you see, that's not a perfect sine wave. The second problem is we have a phase shift in the E mode, in the elastic mode. The elastic mode depends just on elastic deformation of the material, and why should there be a phase shift inside? And the last thing, the dissipated energy should be coupled with a double loading frequency. And as you can see on an experiment made on aluminum alloy 7475, you see the dissipative part we calculated by subtracting the elastic part. It's a sine wave, nearly a sine wave, but just with a loading frequency and not with a double loading frequency. And so we see we have some problems inside this black box. Okay, and then we made a special experiment. We had a pre-cracked specimen. We introduced the crack with a constant stress intensity of 15 megapascals per root meter under fully reversed loading conditions. And then we propagated we continued the test with a constant force, which nearly is the same as the stress intensity we had before, at a loading frequency of 20 hertz, and we had a camera frequency of 293 hertz, and we get these nice images for the E amplitude, E phase, D amplitude, and D phase. That's what you get from the nice black box. And then we made another experiment with the same specimen directly after that, with a loading frequency 5 hertz and a camera frequency of 1000 hertz. So we get much more points in each cycle, and we get the points at the same time of the cycle. And we built a very special diagram. In this diagram, you see just the temperature change on the ligament. That means on the section where you have the cracked tip. And this is the for running time. That means you have the ligament at the beginning, 0 force in the first line. You have here with a maximum tensile stress, you have the temperature on the ligament in this line, and so on, and so it propagates through this cycle. In each point we have about 10, 20, 30 cycles, and we made a mean value of these temperatures. And then we had a look at different points on the crack, before the crack and so on, and looked on the temperature signal, how does it looks like. And you see here along the crack flanks, it don't looks like a sine wave, because in tension you have the crack opening, and there can't be a temperature change because you don't get a load on your material near the crack flanks. In compression, you have a nearly perfect sine wave. That means elastic deformation. On the right side, you see the same in the force. That's the tension part, and in the compression part, and in the tension part, you see just the crack had opened, and you don't get any force on the crack flanks. So we have distinct differences between tension and compression due to crack opening, and you can clearly say a DFT decomposition we cannot apply on this signal. That will not work. When we go to the crack tip and some positions in front of the crack tip, it looks a little bit better. We get in compression nearly perfect sine wave. In tension it's a little bit deformed, and when you look on the hysteresis loop, temperature against the force, you see two different slopes for tension and compression. That's due to the crack opening. And also here we have the problem, different slope in tension and compression. We can only conditionally use the DFT to deselect this signal. When we go far away in front of the crack tip, it looks pretty good. It will be better as longer the distance is to the crack tip. You see nearly the same slope in tension and compression. And in this case, okay, maybe with a good result, we can use the DFT for decomposition of the signal. When we then look on the signal, the measured signal, which we get out of this PT diagram, that means temperature stress diagram I've shown you before, and we look on DFT with 5 modes and with 2 modes, you can see we can clearly describe the run of the temperature at all positions of the crack. Sometimes it's a little bit worse, sometimes it's better, but in a first approach we can use the login to describe the temperature change. But this description does not mean that we can deselect this temperature change into an elastic and a dissipative part. It's just a description of the complete temperature change. And that's the big problem in this field. We thought about how can we do it, and we just said we go and we subtract just the elastic part from the measured temperature change. And there we need another factor for calculating from stresses to the force in this case. And when we do that, you see here the original measured temperature, and when we deselect, when we subtract the elastic part with 2 different slopes, we get nearly the horizontal hysteresis loop, which just shows the dissipative temperature change. That means a little bit warming and again a cooling of the specimen due to dissipative energies. When we go far away from the crack tip, you see we get nearly a closed hysteresis loop because we don't have much dissipative energies, and we don't have much temperature change to these dissipative energies. When we look on the ligament, again to different points, you see at the far away from the crack tip, nearly no temperature change due to dissipative energies, due to plasticity, that it's nearly a horizontal line. When we go near the crack tip, you see here in tension, we get a very steep a steep temperature increase due to plastic deformation, afterwards a cooling down, and then in compression we don't see much temperature change. When we go to the crack flanks, I'm at the end nearly, we have a temperature increase due to dissipation in compression loading when the crack flanks were pressed together. Okay, to the conclusions. Yeah, we have the problem that the log-in evaluation shows that we can describe the temperature change within a cycle, but we cannot decompose it, the temperature change into an E and a D mode. We can do it in an E and a D mode, but that's not the elastic and the dissipative part. And a fully quantitative decomposition of the signal is not possible with a DFT. We can calculate it when we subtract or add the force proportional temperature change due to the elastic mode, but we need different constants for tension and compression loading, and the DFT allows us just a qualitative statement if we have dissipative temperature changes or not. And that's the end, and I thank you for your attention.